Good afternoon. Today we're continuing talking about titrations in our topic of acid-base chemistry, but this time beginning with a weak acid titrating against a strong base. So since we are dealing with a weak acid, we're still starting under an acidic environment, so having a low pH, and our curve shape is going to look very similar to that of a strong acid, except this time things are going to get a little bit more complicated because we have pKa's and Ka's to deal with. But the general shape of our titration curve is going to look the same. As we add base going along the x-axis, our pH is going to start low, acidic, acidic, acidic. It's going to go through an inflection point, which we call the equivalence point, and then it's going to end up being really basic. So first, we need to calculate the pH of our solution of acid. This is before we add any base, and we have 50 milliliters of a 0.1 molar acetic acid solution. The Ka is 1.8 times 10 to the negative fifth, giving us a pKa of 4.74. The way that we solve this problem is very similar to how we've done things in the past, simply with an ice table. We have a weak acid that is in equilibrium with the conjugate acid, or the conjugate base acetate, and the acid hydronium. So we have a small amount of this. There's going to be a shift to the product, and it's going to go back and forth. It's a reversible reaction. So I'm going to abbreviate this ICE and just talk about what happens at equilibrium. So we have a certain amount of acetic acid that we start with, 0.1 molar, that's going to go down by x, and we're going to have acetate and hydronium x as at equilibrium. We're looking for the pH, so this value for x is going to be our target. We're looking for the hydronium concentration. Our Ka is our equilibrium constant, and that's going to be equal to a products over reactants. So we have acetate times hydronium divided by acetic acid. So 1.8 times 10 to the negative fifth is going to be equal to x times x divided by 0.1 minus x, and we're going to ignore that x, giving us x squared over 0.1. We solve and get 1.3 times 10 to the negative 3 molar. Turns out that value is x and x, so we have 1.3 times 10 to the negative third molar is going to be equal to CH232 minus, our acetate concentration. It's also going to be equal to our hydronium concentration. We take the negative log of our hydronium concentration to get pH, and we end up with a pH of 2.89. And again, we're at the very, very beginning because no base has been added. In part B, we add base and calculate the pH after 12.5 milliliters of a 0.1 molar solution of sodium hydroxide has been added to 50 milliliters of 0.1. Our new total volume is going to be the sum of our sodium hydroxide solution and our acetic acid solution. That's going to be 62.5 milliliters. We have a Ka that's still 1.8 times 10 to the negative fifth. Now we're going to need to identify what our acid conjugate base and hydronium values are. So we have HA, A minus, and hydronium. We need our initial moles of acid because we need to figure out how many moles of those have reacted with base. So we can solve that easily by taking 0.1 molar, multiplying it by the volume of that acid solution, which is just 50 milliliters, and we get 5 times 10 to the negative third moles of acid. This is the amount of acid before base has been added. Our moles of sodium hydroxide are added. We need to calculate those. So we have 0.1 molar times 0.0125 liters, that's from the 12.5 milliliters of our base solution, and we end up with 1.25 times 10 to the negative third. We can compare these two values, and we find that our amount of base is less than our amount of acid in moles, which brings us at this point of the curve, somewhere before the equivalence point, because our HA moles are greater than our sodium hydroxide moles. So since we're there, we need to figure out, and we're still under acidic solution, we need to figure out what our concentration of our acid is now that some of it has reacted with base. So we take our 5 times 10 to the negative third moles and we subtract the amount of acid that has reacted with sodium hydroxide, which is 1.25 times 10 to the negative third moles, and we're left with 3.8 times 10 to the negative third moles of HA. Now we can solve for a concentration of acetic acid in our new solution. So we have those moles, 3.8 times 10 to the negative third moles of HA. Now we need to divide by our new total volume, which is 0.0625 liters, because this is after the base solution has been added, so our volume has changed. So our new HA concentration is 6.1 times 10 to the negative second molar. Now we're going to bank that information. Next, we're going to look at what happens to our conjugate base. So our initial values for conjugate base, we have actually already calculated. If this is where we were starting the problem, we would need to do an ice table to figure out what our concentration of A- is, but we've done that already up here. So HA forms A-, so this is our conjugate base, and it's 1.3 times 10 to the negative third molar. We need to convert this to moles before we can add more moles to it. So down here we can look and say that our initial moles of A- is calculated by taking that initial molarity, 1.3 times 10 to the negative third moles of A- over liters, multiply by the volume, 0.050 liters, and we start with 6.5 times 10 to the negative third moles of A-. That's how much A- we have in solution before any of the acetic acid has reacted. What has happened by adding base is we have decreased the amount of acetic acid because it's been deprotonated by the base. The moment that's deprotonated, it forms the conjugate base acetate, A-. So as this value of acetic acid is decreasing, at the same time our acetate is increasing by exactly the same amount. So 1.25 times 10 to the negative third moles of sodium hydroxide have reacted with 1.25 times 10 to the negative third moles of acetic acid to form 1.25 times 10 to the negative third additional moles of acetate. So we need to add that value. So we do that here. We have our 6.5 times 10 to the negative fifth moles of acetate, A-, and we're going to increase that amount by 1.25 times 10 to the negative third moles, giving us 1.3 times 10 to the negative third moles of A-. We now have our concentration of HA, and we can solve for our concentration of A- by dividing by our new total volume, 0.0625 liters. And that gives us our concentration of our conjugate base, acetate, A-, 2.1 times 10 to the negative second. So we now have our HA concentration, we have our A- concentration, and we have our pKa from the table. We have everything we need to solve for pH using the Henderson-Hasselbalch equation. And we do that here. pH is equal to pKa plus the log of A- over HA, which is going to be equal to 4.7 plus the log of 2.1 times 10 to the negative second divided by 6.1 times 10 to the negative second. That gives us a pH of 4.28. So again, we are still before the equivalence point. We have more moles of acid than we have of base, so we should have an acidic solution, and that's exactly what we see. Next, we are going to test and see what the pH is of our titration after 50 milliliters of our 0.1 molar solution of sodium hydroxide has been added. So again, our Ka is 1.8 times 10 to the negative fifth, our pK is 4.74, and we still have this reversible reaction with acetic acid. Our initial moles of HA are still the same. They are 5 times 10 to the negative third moles. What we need to do is calculate how many moles of sodium hydroxide have been added, and we do that here. 0.1 moles per liter times 50 milliliters, that's this 50, equals 5 times 10 to the negative third moles of sodium hydroxide. In this situation, our moles of base equal our mole of acid, so we are at the equivalence point of our titration. So we need to figure out how many moles of HA are remaining. Our initial moles of HA minus our moles of base equals 0, so we have no more acid remaining. So when we are dealing with a point of our titration curve that is equal to the equivalence point or beyond the equivalence point, so any point here or beyond, our pH is dependent on the remaining base. So we need to figure out what's going on with our remaining base. All of our sodium hydroxide has reacted. All of our acetic acid has reacted. All we're left with is acetate. So we need to figure out how our acetate concentration has changed, and we do that by taking our initial moles of acid, 6.5 times 10 to the negative fifth, which we calculated in the last problem. Initial moles of A-, 6.5 times 10 to the negative fifth. And we are increasing by 5 times 10 to the negative third moles because that's how much acetate is being formed. Again, if we have 5 times 10 to the negative third moles of base reacting, that is subtracting 5 times 10 to the negative third from acetic acid, and that is increasing acetate by 5 times 10 to the negative third. So 6.5 times 10 to the negative fifth moles of A- plus 5 times 10 to the negative third is equal to 5.1 times 10 to the negative third moles. So we have gained 5 and we end up with 5.1. So our new A minus concentration is as that value of moles divided by liters, and we use a value that is equal to our new total volume for liters, which is 100. So we have 100 milliliters, which is 0.1 liters. So that gives us 5.1 times 10 to the negative second molar for our new A minus concentration. Great. So what do we do with this value? So now that we have our concentration of acetate in solution, we need to figure out what to do with it. This is where things get a little tricky because we're dealing with a weak acid. The equivalence point for a strong acid, strong base, as we saw in last class, is equal to 7. The equivalence point is not necessarily pH is equal to 7 for a weak acid. The acid has not simply reacted to form water, it has reacted to form conjugate base. So if we were to continue as normal, we would see that acetic acid is equal to 0 molar because all of it's gone. We have 5.1 times 10 to the negative second molar of acetate. If we tried to use the Henderson-Hasselbalch equation, we would have HA 0 in the denominator, and we can't use this equation because we can't divide by 0. So what happens to the remaining CH3COO-, our conjugate base A-? The only two things that are left in solution are acetate and water, and those two things react to form acetic acid and hydroxide. So this is a completely different, well, you can consider this a completely different reaction, which is why I rewrote it and I wrote it in green. If it was simply the reverse of this reaction, that would be a different story, but it is not. We are not reacting acetate with hydronium to form acetic acid and water because there's no hydronium left. All that's left is acetate. So acetate reacts with water to form acetic acid and base. That is a base reaction, so we use a Kb. So what follows is a relatively normal procedure for calculating things, except this time everything's under basic conditions, which is not something we've dealt with yet. But all of the math is going to look very similar. So instead of using a Ka, we're going to use a Kb. And our Kb is going to be still equal to products over reactants, but we have a new equation. In this equation, our products are acetic acid and hydroxide, so those are going to go in the numerator, and our concentration of base, acetate, is going to go in the denominator. We can figure out what Kb is from the autoionization of water. Ka times Kb is always equal to Kw. So our Ka is 1.8 times 10 to the negative fifth, multiply that by Kb, and that gives you 1 times 10 to the negative 14. We can solve for Kb and discover that it's 5.6 times 10 to the negative 10. We have a Kb, we have an initial concentration of one reactant, and we have none of this so far, so we would solve for our equilibrium values using an ice table. It's the same process as before, except this time it's a base. Our numerator in our Kb is hydroxide. That's our target. So we're going to solve for x, and x is going to be equal to that hydroxide concentration, and from there we can get to pH. So let's see how that happens. So we would use an ice table, and we would find that our Kb is equal to our products, which is x times x, divided by our reactant, which is 5.1 times 10 to the negative 2 minus x, but we've ignored the x. We can solve and discover that x squared is equal to 2.86 times 10 to the negative 11, and then take the square root and you get x is equal to 5.3 times 10 to the negative 6. That is equal to our hydroxide concentration, which is our target value. Now that we have our hydroxide concentration, getting to pH is pretty straightforward. You can take the negative log of 5.3 times 10 to the negative 6, and that's going to be equal to POH. Our POH is then calculated to be 5.3. pH plus POH is equal to 14, which again comes from the autoionization of water. And then pH is going to be equal to 14 minus 5.3, a pH of 8.7. So that's our pH at this point in the curve. So this is the equivalence point for this weak acid. It ends up being higher than neutral, so it's slightly basic. Finally, part D, we're going to take a look at what happens after 75 milliliters of that base solution has been added to 50 milliliters of our acetic acid solution. Again, we are at a Ka that's equal to 1.8 times 10 to the negative fifth, a pKa of 4.74, and we have 0 acetic acid remaining. Our initial moles of HA, acetic acid, are still 5 times 10 to the negative third, and what we can do is see how much of base has reacted. So we need to figure out what our moles of sodium hydroxide are. So 0.1 moles times our volume of base solution that's been added, 75, so it's 0.075 liters, gives us 7.5 times 10 to the negative third moles of base. We again compare that to our initial moles of acid, and we discover that we have more base than acid, so we're at a situation that's beyond the equivalence point. We're somewhere up here. In that situation, the pH is dependent on the remaining base. So our moles of sodium hydroxide in excess is what we're interested in. So we take that 7.5 times 10 to the negative third that have been added. We subtract 5 times 10 to the negative 3, which is the amount that is reacted with acid. And we're left with 2.5 times 10 to the negative third moles of sodium hydroxide. So our concentration of excess sodium hydroxide is equal to that value, 2.5 times 10 to the negative third moles, divided by 0.125 liter. That is our new total volume. So when we take that value divided by 0.125, we get 0.02 molar, which is equal to our hydroxide concentration. We take the negative log, and we get a pOH that is equal to 1.7. pOH plus pH is equal to 14, so pH is going to be equal to 14 minus 1.7, giving us a pH of 12.3. A pH of 12.3 should be in the basic region of our pH scale, and it is. We are nice and high up on our pH scale, which makes sense as we are now beyond the equivalence point. Now that we have completed our titration curve, we're going to take a quick look at what happens when we have polyprotic systems. So, for example, a diprotic acid and base. A polyprotic system is one that can donate more than one proton, and a polyprotic base is considered something that can accept more than one proton. So a monoprotic acid would be something like this, hydrochloric acid, which reacts with water to form chloride and hydronium H3O+, which would have a Ka associated with it. A diprotic acid would be something like this, H2SO4, which is sulfuric acid. Sulfuric acid reacts with water to form HSO4- and hydronium. Even if it's not an acid that you've seen before, you can always predict what the conjugate base is because it's losing a hydrogen atom and the charge is becoming more negative as you are losing a positively charged particle. So H2SO4 loses a hydrogen and its charge goes from neutral to minus, which we see here. HSO4 can also act as an acid, so we write a new equation down below, and that reacts with water to form SO4 2-, sulfate, and hydronium. You'd be able to predict that sulfate forms because here we have HSO4, it's going to lose a hydrogen, and its charge is going to go more negative, from -1 down to -2. Common examples of polyprotic system include amino acids. So here we have an example of one in the middle where we have HA. So if we go from left to right as we look across all three of these systems, we have H3N, C with a organic group attached to it, HCO2H. So this is a carboxylic acid group. That hydrogen is the first one to be deprotonated. So this is Ka1 as we go to our intermediate species. We lose a hydrogen and the charge goes down by 1 to a minus in that location. We then lose one of the hydrogens over here attached to nitrogen. So that goes through Ka2 down here. So as you look from left to right, you can keep track of the fact that we're losing hydrogen atoms and our charge is dropping. This species overall has a positive charge. This species overall is neutral. This species overall is negatively charged. So we're losing charge as we go across, and we're losing hydrogens. The middle species would get our typical HA acid abbreviation, but our diprotic is typically written as H2A+. So H2A+ gets deprotonated to form HA, which gets deprotonated to form A-. And we're going to pick up with more about diprotic acids and bases next class.